Welcome to a second video on differential amplifier. In this video, we will see the operation of differential amplifier in common mode, as well as try to find out what is the range of common and differential signal that can be applied, and also find what is CMRR of differential amplifiers. So that for a differential amplifier, if we can also apply a common signal, so in this case we have considered a common signal VIC, which is applied to both the MOSFETs, and we have considered a current source which is typical in nature, having a source resistance of RSS, and we know that because of this applied voltage same in both the transistor, we're going to have current both M1 and M2 in same direction. 1 and 2 are exactly sitting same amplitude of the input voltage, and since we are assuming the dimensions of the transistor to be same, so their transconductance is also same. So we are having current ID1, ID2 in the same direction, so naturally the current will going to flow through. It is exactly the case opposite that in case of differential input voltage, where there was no current flowing through the RSS. Now let's see how does the AC small signal model of the differential amplifier under common mode signal will look like. As we know that for AC analysis we are not supposed to consider, we are supposed to consider the DC voltage and AC current open circuited. Instead of considering a RSS resistor, a single one, we have considered two resistors RSS in parallel, so which happens in RSS. Now the intention of representing two resistors for two parallel is to divide this differential amplifier circuit symmetrically, vertical symmetry. So as we can see now, so this is input voltage of VIC applied to this MOSFET, and this is VIC applied. If I vertically divide, I find out does this circuit look like. The circuit look like exactly this. So when AC ground here, AC ground, we have one more ground, output voltage measured here, the input AC signal applied here. A circuit of CS amplifier with source degeneration resistance, which is in this case it is 2 RSS. The X for the voltage gain of CS amplifier is given by minus GMRD by 1 plus GM into 2, where this 2 RSS has to be the source degeneration resistance. Since we have for a common mode signal, the output gain will be, the gain of the amplifier is totally different compared to the differential input voltage. If you can actually measure what are output voltages V01 and V02, you can surprise to. So both single-ended output voltage V01 and V02 are having negative sign, because both are C amplifier solution. So their gain is minus GM RD plus GM into 2 RSS, which is for single-ended V01, and it is single-ended V02. If you actually find the potential voltage because of one more signal, surprisingly, since these two are of same, they're going to cancel out. Potential gain of amplifier for a common mode signal happens 0. In case of differential amplifier with differential input, one was negative, one was positive, it was actually coming increasing, but here the gain becomes 0 for a common signal. So let us try to identify to define what is this common mode rejection ratio. So it is the ability of the amplifier to the common signal. So we have this differential amplifier. So here only the differential signal, you'll be applying a common signal also. Differential signal, there is a VIC plus VIC applied to both of them. So you will end up with the CMR and as A of the differential by the common. So it is the gain of differential input voltage and gain of the common mode input. So we can define CMRR in two cases, the output and the differential output. If you act out of a single-ended output, you are trying to write expression for the differential voltage is minus GMRD by 2, and the single-ended output voltage of single-ended common signal minus GMRD by 1 plus 2 GMRS. 1 is negligible, so we could able to get the expression for CMRR for a single-ended given by GM into RSS. Whereas if you find what is CMR for a differential measurement, so this is the differential measurement. Now it is D by AC. DD stands for, it is the gain of differential amplifier with differentially applied inputs. Now it is the gain of a common mode differential measured differentially. Here it is applied differentially, but here applied commonly. We know that the gain of a differential amplifier, if it is measured differentially, it is surprisingly, you can see when you measure it differentially for an applied common signal, the gain happens low. So CMRR ID is infinity for a measured output voltage for a differential signal and a common signal. It is a ratio. The gain of the differential amplifier differentially applied as well as differential measured. Here it is commonly applied and differential infinity. So let us spend some time on range of the common mode input that can be applied so that your differential amplifier is working properly. As we can see now, so this is a circuit diagram of that differential amplifier with signal applied here. Since you can see it is CM onto the both the gates, and you can see this is gate to source voltage and this is source voltage, that is the voltage at the source. We can write by KVL. The VCM can be written as VGS plus VS. So in equation I can write VS, that is the voltage at the source is given by VGS, and we can also define what is the voltage at the drain one in terms of VDD a drop of current. So it can be written as this expression. So we know what the voltage at source of MOS M1 and drain of MOSFET M1. So if you know the drain and source voltages, then we can find what is the VDS, that is drain. So it is given by this expression minus VS. So you are trying to substitute what the voltage at drain and what the voltage at source. Upon simplifying, so you will get VDS is this expression. I can see as you keep on increasing the common mode voltage, the VD remains constant, but this VS is keep on increasing. So if this common mode voltages reaches such a point where this VD, as you can, so this common mode voltage will become some range which we call it as VCM max. Then VDS becomes VDS sat equal to VOV. So substituting in this expression of VDS is equal to VDD minus I by 2 RD minus VCM plus VOV plus VTH. Substitute this VDS equal to the maximum possible input voltage that can be applied. This differential mode is given by VTH plus VDD minus I2 into RD. So we cannot apply any voltage beyond this. If we apply any voltage beyond this as a common mode voltage, the transistor will go to linear region. So then whatever expression we have written for common mode will not be valid. Similarly, we can find what is the minimum common mode input voltage that can be applied. So as you know that this is again VGS, so we can write this VCM as the voltage VGS required to keep this in saturation, and this VCS is nothing but as the minimum voltage that should remain at the this current source, but it can deliver a current of I. And this is again minus VSS, which is the supply voltage. Now I'm going to write a KVL in this loop. So VCM is equal to VS plus VCS, which is voltage to be maintained just to keep a current of I flow all the time, and of course the minus VSS. So VCM minimum happens to be we are splitting this VGS as VOV plus VTH, is VOV plus VTH, VCS minus VSS. So we cannot go anything less than this voltage. So the current source will no more offer a current of I. Similarly, we can find the range of input voltage that can be applied. So as we can see now, this is input is grounded, the input is applied with VID. So as per the equation, we can write VID, that is the applied voltage nothing but VGS1 minus VG. So meaning this plus minus VGS1, this is minus, this is plus VG2. If you write the KVL equation for this VID in terms of VGS1 and VGS2, it could be this expression. That the current flowing through the transistor M1 and M2 is equal to I by 2, and it is given by the expression Kp by 2 done into VGS minus VTH whole square. So we can express VOV in terms of I, Kp and the dimensions also. As we can see here, as VID increases, so VID is naturally the drain to gate to source voltage. If the gate voltage increases, naturally the current ID1 has to increase. If this ID1 increases, naturally this ID2 has to reduce. So why this has to reduce means because the summation of both the currents should be equal to I. So because of this increased gate voltage, so naturally drain current of this will increase. So when this drain increases, naturally this current has to reduce because the summation has to. Let us see how long we think. So one of the possibilities that we know that this is I by 2, I by 20 voltage. This I by 2 can reach equal to I. So our current which was flowing through and I by 2 can become 0. When this current becomes 0, so become full I. The entire current which is flowing through M2 will be transferred to M1. So we are trying to find out what input voltage that condition exists. So then some VTH. So when the VGS of this becomes equal to VTH, then the current here becomes 0. When the current becomes here, then naturally the entire current will be flowing through this M1 transistor. So that's what we are trying to establish here. So is equal to ID is equal to VID max when ID2 becomes, so that is VGS2 should become VH. For drain current of second MOSFET to become 0, we should have a gate voltage at the M2. Gate to source voltage should be exactly equal to VH. This ID2 is 0. Now why this is 0 means if you substitute VGS as simply VTS, so naturally the current will become 0. Then what is this ID1? So since ID2 has become, the entire go through transistor M1 only. So we are supposed to find out what is VS1 for the current through the MOSFET 1 to be equal to I. That be written this we are trying to write I equal to Kp by so on. So from this you can write VGS1 which is equal to VTH plus root of 2I by Kp into W by L. But you might have seen in the previous case an expression. So this expression VOV is the overdrive voltage for this transistor to have current of I by 2. Suppose if a current of I flows, so then that will be different. Now we are trying to find out here, as you can see here, this we are trying to replace. We are trying this expression of I by Kp into W by L of 1. So this in this expression we are having the root of I by Kp into W by L. We are replacing it by VOV. So replace that by VOV, then VGS1 will become a VTH plus root of 2 into VOV. So meaning if a current of I has to flow through MOSFET M1, the VGS has to be VTH plus root 2 times of VOV. So then this expression VID max is nothing but GS1 minus VGS1 minus VGS2. So when this VI become max, so we know that VGS2 has to be VTH. The corresponding VGS1, which will have a current of ID is equal to I given by H root 2 into VOV. So you can simplify this. This VTH will go with this. So VID will become equal to root 2 times VOV. Meaning, if you keep on increasing the differential voltage that is up to the differential amplifier, the current which was flowing through M2 will be get transferred onto M1. The current at M2 becomes 0. The entire current will flow through M1 only. Similarly, we can derive the minimum drain current, minimum differential voltage that can be applied minus root 2 times VOV. The entire current of M1 will be transferred onto M2. So that's what is shown in graph is differential. So as you can see, when you are not applying any differential voltage, both the transistors have a current of I by 2. If you apply positive voltage, MOSFET of first MOSFET, that is M1 MOSFET, is having an increased current. Naturally, the M MOSFET is going to have a reduced current. So as you keep on increasing voltage to a large value, at some point current of M1 will become I. Simultaneously, the current M2 will become 0. This is the ratio of ID by I. ID1 by I will become 1, meaning ID1 is equal to I. You can see ID2 by I happens to be 0, meaning that no current is flowing through second MOSFET. That input voltage at which this happens is the voltage where it is VID max, which is by root 2 times VOV. So this is root 2 times VOV. Similarly, as you reduce the input voltage in the negative direction, so this input voltage of ID MOSFET M1 is using and it will become 0, whereas the current of M2 is on increasing, it will become equal to I. So that will happen when it is minus root of VOV. This is what is minus 1.4. Here it is plus 1.4. So this is the range of input voltages where the entire current flowing through one of the transistor will be transferred onto the other transistor when you apply a positive voltage. Similar thing will happen by negative voltage, so it will be transferred onto the other transistor. We'll see further analysis of differential amplifiers in the coming weeks.